All right, let's get started. Today we're going to keep talking about dynamical systems. And last time we did a little bit on dynamical systems in terms of the controllability of linear systems. And we're going to keep, I'm just going to actually go over that one more time a little bit in case it wasn't quite clear from last time. And then I'll talk about partially observable systems. This is the case where we no longer actually know the state anymore. We don't have full information of the state xt, but we only observe some function of the state. And this is really common in practice because oftentimes there are certain elements of the state that are clearly important, but they're really hard to measure in practice. We'll talk about then a little bit separate topic about differential algebraic equations. These are differential equations. This is continuous time differential equations that where in addition to just the differential equation part, you also have algebraic equations. You also have equality constraints, typically nonlinear ones. As we'll see, if they're linear equalities, then you can just reduce it to a differential equation directly. But if they're nonlinear, then you actually have both this differential part and this algebraic part. And this is actually how you express the evolution of generators under power flow. And so it's worth at least seeing these things. We won't actually solve much of them. We'll really look at these only in the case where the algebraic equations are linear. And in that case, they just become differential equations. So it's really just the same as continuous time dynamical systems. But it's good to know about these at least, because we are going to sort of, you will see them if you see power flow joined with the differential equations of a generator. And finally, I'll talk very briefly about Markov decision processes. Really, I'm only going to introduce notation this time because this whole lecture is more about the systems themselves and not about the control of the systems. The next couple lectures will be about actually controlling systems like this. And so because of that, I'm really going to focus on just the definitions here. And next time, we'll talk about how you actually go about solving MDPs. So first of all, were there any questions from last time? I'm going to go over this controllability issue again because I think I was a little bit fast last time. But were there any general questions from this or from other elements? OK. So the basic idea here is that we have some linear system. And I'm going to think about it in a discrete time sense. The exact same considerations apply for continuous time, too. So we have some system, xt plus 1 equals axt plus b ut. We can actually have this be an affine system if we want. We can add an extra constant here. It doesn't change any of this math. And now we want to ask the question, if x1 is, say, x1 not, just something given to you, and I want to say xt for some time t equals x star, where this is also given to you. Maybe I'll call it like xt star. When this is also given to you, the question is, can I go from this state to that state in t time steps here? And in fact, I'll even say, let's not even worry about what t is. Let's just say, can I go to this in any number of time steps? So I'll just sort of make this like x infinity here. Given any number of time steps, can I get to it? And in fact, it'll turn out that we don't need to consider any number. If you can do it at all, you can do it in a finite number of time steps. So the way you can look at this problem is essentially you don't have control, really, you can't directly set the states, right? These are things that are governed by the system and we're given a fixed initial state. So all you can do is pick the controls that will hopefully guide you toward this other state. And if you write out what the state evolution will be, what we saw last time, right, was that we have something like x2 equals a x1, but that's ax1 0 plus b u1. I guess I don't put the 0 there. I just assume that x1 is fixed here. And then if you keep doing this, you'll have something like x3 equals, well, it's ax2 plus b u2, but that equals a squared x10 plus a b u1 plus b u2. And you can keep doing this, and what you get is you get an equation where every state is determined by a function of this initial state here, and then some functions of all the controls you've applied up to that point. Right? So we're basically just eliminating x2, x3, et cetera, from this equation. And we can write this in a big matrix form, which is exactly this thing. If you sort of expand this, what you'll get is you'll get that xt equals, well, there's this first term. I use there a k. So a xk plus 1 equals a to the k times this guy, x1, plus a big function of all your controls. And I'm putting this in a single matrix here just to sort of make it obvious what's actually happening here. But this is just a big matrix here, which will be something like a k minus 1b, a k minus 2b, all the way just to b, times a vector of all my controls, u1, u2, all the way to uk. OK? And now the question is there a solution to this linear system or not? This is now a linear system, right? We have some set of linear equations. There are, in this case, n unknowns, right? Because x is n, always assume that x is n-dimensional. And we have, maybe I'll just write it here. So we have n, well, sorry, this isn't unknown because we're sort of giving it a fixed thing. But what we have is we have n systems of equations. So we have n equations. And we have k times m unknowns. Okay? So if k here, k times m is bigger than n, then we can maybe sometimes solve the system or not. All right, and the way we do this is that this here, we talked about before, right? This is a n by km matrix. I'll call it, I think I called it C last time, like a script C. Something like this. And if it has at least n independent rows, what we can do is we just take those rows, right? We take all, sorry, n independent columns. We take all the columns, something like this, like a little MATLAB-like notation. Take all the columns, and we look for some subset of rows here, where the size of this subset is equal to n. And now we would just invert this matrix to find the solution, right? So, we have essentially x star equals a k x1 plus this guy here. A little bit too sloppy in terms of writing it there. C script this guy I times u, whatever u hat, where it's important I'll just remember like this, u I, something like that. Where it's important to know that what I mean here by this u, that's the u bar or something like that, this u is the concatenation of all those u's. I'm looking only at the ith, at the some index of I of these. Now, unlike the homework with the power flow, you don't necessarily know what this index I is here. You can actually choose it to be whatever you want, as long as the columns, those I columns, those n columns of C are all independent. And the reason why you need that is if these are all independent, that means you can invert this matrix, and then this will just have a solution, right? It'll just say that ui equals C inverse times x star minus a to the k x1. Right, and that will give you the actual sequence of controls you execute to go from this state to that state. And all the rest are 0. All the other controls there are 0. Okay? So you really just have to activate, execute some control, execute n different elements of that control. Now, this crucially hinged on the fact that I could find n independent columns in this C matrix. Right? If I can't do that, then I can't invert this matrix anymore. And so there may not be a solution that actually brings you to that state, that control. Sorry. there might not be a solution of controls that bring you from this state to that state. Okay, so it really, really depended on this matrix having n independent columns. And it turns out that, and so the way you decide, if I can go from x1 to xt in t time steps, is you form this big matrix, right? All the way up to a t minus 1, etc. Look at all the controls and see if there are, in fact, n independent columns in this matrix here. It turns out, though, that for a kind of very fundamental but also not that easy to show property of matrices, you don't need to actually go up all the way to t. You can actually go up all the way to only to n here. We're not going to worry about that, but basically you don't need to go up to, you don't need to form sort of an infinitely big matrix here to test it. You just form up to k, a to the n minus 1 all the way down, and that's actually sufficient. And that comes from the fact, this is just sort of a side note because you don't really need to know this for the problems that we're going to deal with. I don't want to erase this too much. But this comes from this very interesting property called the Cayley-Hamilton theorem. And what this says is that it says that a to the n, where a here is n by n. So a to the n, a raised to the nth power, is some linear combination, sum from I equals 1 to n, 0 to n minus 1, of some coefficients ai times a to the I. Sorry, alpha I times a to the I. So basically, you can take the first n powers of a matrix, this n by n, and express the nth power in terms of that. This is actually not that easy to show for general matrices. If you can take eigenvalue compositions, it becomes a lot easier to show. But in general, it's not that easy to show this thing. It's not that hard either, but it requires a little bit of math. And of course, it also means the same is true for higher powers, right? Because if this is a linear combination, then so is n plus 1. So it's true for all higher powers of n as well. And so you can essentially just break, because the higher powers are also functions of this, but this is a function of the other ones, and so you can keep doing it. And so what this means is that you don't need to go up to infinity here in the size and the number of a's you take, because adding more than n won't actually give you any new information. It won't generate any more independent columns because they're all linear functions of the past ones. And so you don't have to worry about that. You just go up to size a to the n minus 1 here. It doesn't really affect things. You can always just sort of keep going higher and see when the rank stops increasing, for example. But sort of a nice property to know that actually you can test kind of the absolute infinite time reachability and controllability of these systems without actually looking at an infinitely large matrix here. Okay, so this is sort of an aside. Don't worry about this too much, but it's an interesting little fact. All right, so the other property, are there any questions about this, the controllability part? Yeah.
I mean, is this related to like Markov chains and regression?
So I think that, so Markov chains, the way Markov chains are usually described is Markov chains are things without control. A Markov decision process is something with control. So this is not really the same as the properties of a Markov chain. What's more similar to properties of a Markov chain is actually the next thing we're going to talk about, which is stability of these dynamical systems. But it's important to know that these are not quite the same as Markov chains, because dynamical systems, the state here is a general vector. Doesn't have to be a probability distribution, say. And so Markov chains, in some sense, are actually a very special case of dynamical systems like this, where your state vector is always a distribution, essentially. So, of course, there are a lot more properties of Markov chains in addition to that, but that's sort of one way of looking at this, at least. Okay, so this is one sort of big property of linear systems, was this question of controllability. Can I reach other states? And that's very important, because if you can't reach any other state, you have a very, sometimes you can't do anything, right? There's just no way I could control the system to where I want it to be, so I can't really do anything. Another very important property of linear systems is this notion of stability. And what stability asks, so controllability asks, can I get from state A to state B? What stability asks is for a fixed controller, so now I have a control law saying uk equals k of xt, sorry, ut equals k of xt, k times xt. I can look, okay, so actually let me make this start from the beginning again. So if we have a system like this, and I also have some controller that prescribes my teeth control as a linear function of the state, then you can actually write this whole system as xt plus 1 equals a tilde xt, right? Where a tilde here is just equal to a plus b times k. So given a fixed controller, a linear dynamical system like this, a controlled one, will look just like this, which is a dynamical system now without any control. This is called an autonomous system. If you're not executing control, of course, here you really are executing control, but the system with control in the loop is just called an autonomous system. Well, this is called an autonomous system, and typically you call it autonomous when the form does not have an extra little control term there, even if you're in practice actually executing control. And a big question about these autonomous systems is the question of what happens to the state as you keep applying this thing. Right? So, if x1 is just given, then x2 will obviously equal a tilde times x1. X3 will equal a tilde squared times x1. A4 will equal a tilde cubed times x1, etc. Right? So the question is, what happens to these states? You're sort of multiplying them by bigger and bigger powers of this a tilde matrix. What's going to happen to this thing? And we covered this a little bit when I first talked about eigenvalues. But the basic idea here is one called stability. It's the question, and there's really only two options. Well, there's sort of an exact possibility for one other option, but it's in practice you wouldn't see it as much because it has to be kind of perfectly well, I'll say what I mean first, and then we'll get to that. So essentially, the question is, how do you know what happens to this state here as you keep going, keep applying this matrix? And for the most part, there are two possibilities. Either it will go to 0. You will have 0 state, right? Because if the state is 0, then you just keep multiplying 0 by matrix, but it stays at 0, right? So actually, if it ever goes to 0 at all, it's going to stay at 0. But if it's a little bit away from 0 and you keep doing this, either it could go to 0, either it could sort of tail off to 0 and your state just goes to 0, or it will actually keep getting bigger and bigger, the state. Now, there, of course, are cases where some elements will get bigger and some won't. But the typical case is that all the elements will either go to infinity or they will all go to 0. And the way you analyze this type of system here is by looking at the eigenvalues of this matrix. So when we talked about eigenvalues, I think that first little review on linear algebra, we don't use them too much in this class, but this is actually a great example of eigenvalues, and I actually talked about it a little bit when I talked about eigenvalues the first time. The way you can analyze what happens here is you can look at the eigenvalues of A. So I'm going to write A in terms of its eigenvalue decomposition here. S is a matrix of eigenvectors. Lambda is a matrix of all the eigenvalues of A as a diagonal matrix. And so this is the eigenvalue form, the eigenvalue decomposition of A tilde. And this eigenvalue decomposition makes it very easy to analyze what happens to higher powers of A, right? Because A, k to the tilde, well, we just start repeating this, right? You have S lambda S inverse, S lambda S inverse, dot S lambda, right? S lambda S inverse. But these guys will all cancel out. All these S inverse S terms will cancel out. So this will equal S to the lambda to the k S inverse. But importantly, lambda is a diagonal matrix. So the diagonal matrix to the kth power is just going to be the individual diagonal elements of that matrix, each raised to the kth power. Okay? And for a scale, so really we can now analyze what happens to this matrix as a function of what happens to the eigenvalues of the matrix. And in particular, if all the eigenvalues have absolute value that's less than 1, strictly less than 1, then they will all go to 0. So if lambda I is greater than 0, this implies that lambda I to the k, this will go to 0. And if it's true for all of them, this means that this whole matrix goes to 0. And so xk will also go to 0. Right? The sort of the case that I mentioned before was the case that this is exactly equal to 1. Then you can have some subspace that sort of always stays at some value. This is actually exactly what happens in a Markov chain, because in a Markov chain, these things always have to be probabilities. And so they always have to sum to 1. And so you actually have always an eigenvalue exactly equal to 1. But for a lot of linear dynamical systems, especially if you add a controller, and you can add arbitrary controllers, and they can, in fact, take on, the control can take on arbitrary values here, you'll typically have either the system has an eigenvalue over 1 or less than 1. If it has an eigenvalue greater than 1, then that, so I guess I should say if this for all I, that will imply that xt will go to 0. If, on the other hand, there exists just one lambda such that lambda I is greater than 1, this means that xt will go to infinity. And typically, it doesn't have to be this way, but typically all the values will go to infinity because you're multiplying it first by this s term. So essentially what you do is you multiply first by this s term, then you, maybe if only one, say only the first eigenvalue is equal to greater than 1. So all the rest will go to 0, but that 1 will just keep getting bigger and bigger. What you would do is you would first take xt or x1 times this guy. Right. That's say still a full vector. Then this next multiplication would zero out all but the first entry of it. But then when you multiply again by this, you would get a full vector again. So essentially, typically, what you'd see, assuming there's no structure of these matrices, what you would see is that all the elements of x would go to infinity. Now, this sort of raises some interesting questions too, right? Because you might imagine, and we're not going to talk about this at all, but you might imagine, right, that if the component of this term that multiplies by that bigger value actually starts off at 0, even if x1 itself is not 0, then you're actually OK, right? Because then everything's fine. So there actually are some weird invariances, or not weird, but there's some interesting invariances here, where if you start out in certain spaces, certain subsets of the state space, you actually can still go to 0, even though the matrix is unstable. But we're not going to worry about that. We're going to think about the cases, because then usually what happens is, a very small perturbation away from that space will still make you go to infinity then. So we're going to typically think about cases where either all the states go to infinity or all the states go to 0. That's typically the cases we'll talk about. And you can get that by analyzing the eigenvalues of the matrix. Now, it may seem as though this is a fairly limited set of principles we've talked about here, right? Because we're talking about linear systems only. We're talking about systems of this form. And there are some that act that way. I guess nominally that heating and cooling, right, in a building follows a linear dynamical system. So maybe that's perfectly useful. They are very useful in practice. But it's certainly also the case that not a lot of systems seem linear. In fact, if you get very philosophical here, no system's really linear, right? Because there are fundamental linear systems have no limits, right? If one term is velocity in a linear system and it's unstable, velocity will just keep going higher and higher and higher. And we know that the universe doesn't allow that velocity to keep increasing exponentially. So in some fundamental way, no system is really linear. And so it's a question of how is this really that useful? And other than just being a very good approximation sometimes, it's very useful because we actually can use the theory of linear systems to analyze nonlinear systems. And we can do this in a fairly exact way. What I mean by that is, suppose we have some nonlinear system, xt plus 1 equals f of xt and ut. This is now a nonlinear function. It does not have to be in that form. And also suppose we have some equilibrium point, I'll call it. This is a point where there is a, essentially you have some point x star such that if you start in x star and apply some control u star, you stay in x star. So if you're at that point, you will and keep applying that control, you'll stay there forever. It turns out that we actually can analyze exactly, not approximately, but exactly, the controllability around this point, the controllability and stability around this point, by looking at the linear approximation to this point. And what I mean by that is we form a linear system where our state is really, I'll call it x hat, is really equal to x minus x star. So it's the difference away from this equilibrium point. And our A and B matrices are, when we form the system A xt plus 1 equals A xt, x hat t, plus B u t. Actually, I should say u hat also is u minus u star. So we're talking about sort of differences in the state and in the control. So, and we can form this linear system here, which describes approximately how this difference evolves as a function of difference in control. And where these A and B matrices here are the Jacobians of this nonlinear system with respect to x and u. So here A equals the Jacobian with respect to x of this guy evaluated x star and u star, and B equals the Jacobian with respect to u of this same guy. And what's really amazing here is that this, if you analyze the stability and controllability of this system, this, at least in the formal definition, is in a small enough region around that equilibrium point, where it can actually be very, very small depending on how nasty that system is. But there is some actual finite region around that point, or some non-zero region, I should say. Definitely finite, or could be infinite, I guess, but it's definitely non-zero. There's some non-zero region around that point here where the stability of this nonlinear system is actually exactly given by the stability and controllability of this linear system. So that's, and again, we're not really gonna talk too much about that. You won't have to use this to analyze nonlinear systems, but this is a really important point to kind of know about, that actually these tools are very useful for nonlinear systems as well. Okay, are there any questions about the controllability and stability? Okay. Now let's move to another topic, which is this idea of partially observable systems. So remember, we've been talking about thus far systems where we are actually allowed to use some control law like this, right? Because, well, we are assuming implicitly when we write a control law like this that we can actually observe what the state is, right? The actions are the things that we take as the agent in the system. And so when we write a control law like this, we're saying, well, we just look at the state and then multiply it by this k matrix and then take those actions. If we don't know what the state is, it's not clear that we can do this, right? How do you do that if you don't know what the actual state is? That's very unclear. And in many cases, you actually won't know what the true state of the system is. Right, so a common example is that maybe it's easier to know your position if you're driving, say. Well, maybe that's actually the opposite thing that we want exactly. But say something, if you're the example I used for partially observable system was, if you're a ship in the ocean, you might not know your absolute location. Though now I guess you can with GPS, so it's becoming less of a wonderful example for all control classes. You don't know your position, say, but you do know a distance to different beacons, right? So if you're somewhere here, You know the absolute location of this guy, A, and you know the absolute location of this guy, B. And all you actually observe is this distance here. Right? Well, you don't necessarily know actually where you are. Actually, maybe I'll just do it with 1. It's a little easier to see at a time. So if I have some sort of fixed position, x0, and I am here, this is my state at xt, and what I actually observe is just this distance here, d. I don't know where I am globally, right? Because I could be anywhere along this entire system here. And maybe there are others that I don't observe because I'm not close enough to them or something like that. So if you get enough measurements, you can maybe figure out where you are. But short of that, you don't really know where you are in this thing, because you could be anywhere along that whole manifold. If you have 2 and you're constrained in a plane, you could be at 2 points, right? You could be sort of up one side and the bottom. If you have 3, then in the plane, at least you know where you are. So it's very common. And maybe another example would be something like our room example, where we have 4 different rooms, and the state is the heating in each of these rooms, or the state is the temperature in each of these rooms. But we only have a little thermometer, in 2 of the rooms. The rest of them don't have thermometers, so we don't know what the actual state is in those other ones. And the question is now, well, now what do we do? Now how do we go about controlling the system? We don't know what the state is. The typical approach here, you could do a bunch of things I should add to. One thing you could do, so the cases, we have the dynamical system where we have, I'll erase this. We're no longer talking about linear systems alone. With the dynamical system, f, x, t, ut, where what we actually observe, yt, is some function of the current state. It could be a function of the control too, but we assume that we know the control, so whatever. We'll just make it a function of the state. And it's usually the case also that the dimension of this, yt, is a vector in Rp, and we usually assume that p is less than n. And that h is not invertible. If h is invertible, basically if p is equal to n, say, and you can just invert h to get the state, then you just take your observation, you invert the state, or invert the measurement function, and you get your state. So you effectively do know your state in that case, and there's no real interesting elements to this. What's interesting is when the dimension here, or even more formally, kind of the true information, because you could have repeated measurements here that wouldn't actually help you, but the actual information you get about your state is less than the size of the state itself. So we're assuming that you can't just figure out what the state is in one step by looking at your measurement. So what this means is we cannot directly get x given y. And so the question is, what do we do? Well, I should add, we could do a lot of things, right? We could just say, okay, well, let's just take, let's not worry about it. Let's just assume that our control is now a function of y. This is called output feedback controllers. And that actually you can do that. You can just ignore the fact and just treat y as being what you control based upon. That can work fine sometimes, actually. But the more common strategy here is to actually use your knowledge of the system itself. So we're going to assume that again, here this whole time, we sort of know what f is and we know what h is. And so we can actually use our knowledge of those matrices and those functions and these things that we observe, the vectors we observe, to actually estimate what the state is, given our observations. And this is a technique known as state estimation, as filtering, it has a lot of different names. The basic question is, given not just one state, because we're assuming that we can't do it with one state alone, but given with one observation alone, so if we just have one observation, we can't do anything. But given many observations, say you observe things from time 1 to time t, can you then determine what the states are? Right? And this is the question of what's called state estimation or filtering. And in the case here, which is actually a deterministic system, so we assume that the state evolves exactly like this. And that introduces us to a very easy problem, right? Because if we were to know the first state then we know the controls we apply, right? Because those are the things we actually do. So if we were to know the first state, we actually would know all the subsequent states. So really, for a deterministic system, filtering takes the following problem. Essentially, the problem is, given y1 to yt, say, I have actually a, I guess I'm using yk. Can we find what our first state was? With the understanding that this, then we can find all the subsequent states as well, because we can just plug them into our equations then. Right? And so we're given all these observations, we want to find the first state. And much like the case for controllability, this becomes a set of equations, essentially. Okay? So we can form all that we know, when we know all the y vectors. So what we really say is that we know y1, y2, all the way to yk. And this is some big function. I'll write like this. I'll write like h bar of x1, right? These things are all going to be some function just of x1, and then also, I guess, of all the controls we take too, of u1 to uk. But those we know. So the only thing we don't know here is x1. The question is, given this, find x1 that satisfies this equation. Okay, this is just back to nonlinear equation solving. We can just take Newton's method or wherever we want and find the x1 that actually satisfies this equation. Now, in general, what's the size of this going to be, this matrix here? Vector, sorry. How big is it? How big is each y? Right, so how big is this whole thing? Right, so there are kp knowns, and then there are n unknowns. So again, just with controllability, you can as with controllability, I should say, you can imagine that as long as this is bigger than that, you might have a chance of figuring this out. Now again, this is nonlinear here in the general case. So there's lots of subtleties. Newton's method might not work. It could be that there's no solution even though there's more knowns and unknowns. It could be there's no solution because maybe you weren't quite right with your dynamics, or you weren't quite right with your no measurement function. So there actually is no solution given the ones you know. But in theory, we can do this. Well, at least I shouldn't say that. In theory, it seems possible that we can do it, subject to the fact that Newton's method might not actually work for this. So what we can do, though, is again, rather than thinking about the full nonlinear case of this question, we just look at the case of linear parts of the observable systems. Okay, so now we're going to take the step back to linear systems again, much like we did for control. We're doing the same thing for observation and state estimation. And so the idea is here we have a linear dynamical system where the observation is also a linear function of the state. And we'll assume here that C, so C, actually, what size would C be? Yell it out. How big is C? What was that? How many rows? How many columns? OK. So C is p times n, and we're going to assume that p is smaller than n. And we'll assume for this case that this is a full rank matrix too, so the rank is equal to p. That means you get p independent measurements. So for example, the case I had before where we had only two thermometers in the room, where we have 4 rooms like this. The state is the temperature at each one. But we only have thermometers in this one and this one. draw a little thermometer there. What this would say is that yt equals, oops, I should have an xt there. Doesn't equal that, it equals that times xt. So yt equals this. It equals, well, we know yt is a vector in R2. And it just corresponds to the temperature in the first one and the temperature in the second one. So we observe this one and that one, and we don't observe the others. You could also have some kind of weird measurements here where maybe, you know, each measurement is some linear combination of all the different states. I don't know why you would do that. But maybe you could imagine a thermometer that was like right on the boundary of two walls, so it actually was affected by the state in both rooms. And it was an interesting combination of the state temperature in both rooms. But we'll just look at this sort of simple system here. So in this case, the question now is, given this system and this observation, can I figure out uniquely what the first state was? Because if I figure out the first state, I can figure out all the states. Right? And in fact, let's just worry about the case when we don't have any controls at all, because it can be easier than, you know, you always can add controls. You know what they are. You know how they're affecting everything. So let's just ignore that fact and just think about the case where we don't have any controls at all. So in that case, what we have is the following. And I'll actually wait off till so we have this. Xt plus 1 equals a xt, and yt equals c times xt. OK, so we want to find x1. What we have is y1 through some number of y's. OK, so I'm going to write now that sort of specialization of what that thing was, this vector here for the linear systems. So what is y1 equal to in terms of x1? So y1 equals some function of x1. What is it? Right. OK. Makes sense, right? So now y2 is also a function of x1. What is it? Yes. Did everyone hear that? Do you know? So what's y2 as a function of x1? Ignore it. So just look at this. Don't know where they're used there. So what is y2? Actually, just in terms of any of the states.
Y2?
Yeah.
CX2.
Right. So y2 equals c times x2. So what's x2? How,
AX1, which is
yeah. So x2 is ax1. So this equals c ax1. Right. That's right there. ax1. And what's y3? In terms of x1, what's y3 in terms of x1? So what is y3 period? I mean, what?
CX3.
So yeah, so y3 is cx3. So what's in terms of x1 then?
So AX2 and then x2 to x1.
Mm-hmm.
So C, A, B.
Wait. So close. So it's C, A. What's the next thing?
2a squared x1.
Right. There's no other c there. I mean, you couldn't have that because you only observe it once. The states just evolve according to a to the whatever times x1, and then you get those. So this actually looks really similar, right, to what we saw before. So this whole thing is, I'll just take off the x's here. This whole thing is equal to all this times x1. Okay? So this should look, and it is exactly the same, in fact, as the controllability matrix that we had. And this guy is often called the observability matrix, written as a script O. Not very good at writing scripts, I guess, on O's. And so the question now is, I know these things. I know this because I know all the matrices, and I don't know that. So when can I find this, given these, and this? So let's maybe first talk about, we'll make this a little more concrete. Ca to the k minus 1. Okay? So first of all, how big is this matrix? This O matrix? What's the size of it? First of all, how many columns is it? That one's easy. Yeah, it's n columns. How many rows is it? Yeah.
This is the same situation as before, right?
Yeah. So actually, maybe then, how do you go about finding x given all these y's?
So I guess you have to invert.
Right.
And so there's a bunch of n independent full rank. Basically.
Right. You need to find n independent rows now, though. Important, not n independent columns. You need to find independent rows. So you form this thing. You search for n of the independent rows in it, and you invert that to find x1. So this is sort of a really nice, and then actually I had this all on the next thing. And again, the same considerations as before. You actually don't need to form the whole thing. You just need to form the first up to the power n minus 1 here, and that will actually tell you if you can ever estimate the first state given all the ones in the past. Now we'll talk about in a second stochastic systems. I should probably put that on the board in the first place. But in stochastic systems, which stochastic systems, remember the very first time I introduced these at least, they were systems where there's some additional noise term in addition to just the dynamics of the system, right? There's some noise term here that you also add. And in that case, it is no longer the case actually that you can ever know what the state is exactly. Right? Because you don't have enough information to figure out what the state is from a single measurement, and there's some randomness suggested every single time, so you can never quite exactly know what it is. It turns out what you need to do is you actually sort of form a running estimate, and you keep estimating based on something very similar to this. In the case of a linear system with Gaussian noise, this is called a Kalman filter. We'll talk about that a little bit more later on. But essentially what you do is you keep doing a process like this that takes into account the uncertainty of the state and tries to kind of form better and better estimates, even though you can never actually get it exactly. That's sort of the basic principle here. So, but for these cases where you have a deterministic system, you actually can compute the state exactly, because you can figure out from everything going on what is the first state, and then from the first state you can compute the subsequent states. So the next topic, and actually, so I may have to just pause for a second. Are there any questions about this part? Okay, so let's go to this next part here, which is talking about differential algebraic equations. So we're going to make the move back now to continuous time from discrete time. And this is a little bit of a departure because we spend most of our time in discrete time land, because we're talking about computers here, and computers have to simulate these things with some numbers, some sense of discrete intervals or something like that. But we're going to talk about continuous time again, and what we're going to do is talk about the way you represent things like power flow when you now take into account the dynamics of what generators do. And as I said, formally what these things are, differential algebra equations they are equations where you have both a differential equation part, that's the continuous time dynamics, as well as an algebraic part. So I'll write it like this. Here I'm actually abusing notation a little bit here. We're only going to worry about fully observable ones here. We're not going to worry about the observations here. And I'm actually using P now to talk about a different vector Z's dimension, but sorry about that. We run out of letters kind of quickly. Maybe we should use Q or something like that for it. But anyway, we have some set of variables here. So we have normally, as before, we have our state variables x in Rn. And we also have what I'm calling Z in Rp, which are what I'm calling the state algebraic variables. And these are the variables that we don't actually get derivatives for in our dynamics. They are only given in terms of having to satisfy certain linear equations. Sorry, certain nonlinear equations. So as before, we have so we have now two state variables, and also as before, we have our control U and Rm. So as before, we have a differential equation. So it's saying the time derivative of x equals some function of all the state variables here. This is our continuous time dynamics of these variables x, these x variables. We also have a set of nonlinear equalities, which I'll write as 0 equals g of x, z, and u. Where here, both of these are mappings from, well, f is a mapping from all these inputs to Rn, because it gives the time derivatives of the thing. And g is a mapping for all those things to Rp, because in order for there to be the right number of knowns and unknowns, we have to have exactly p equations here. Okay, so this is a little bit trickier, right, than differential equations, because, and one way of seeing this is, if we want to simulate this system, it's actually kind of a little bit trickier. When we had a system like this, when it was just x dot equals f of x, then we can write the discrete time kind of simulation of this thing, right? We can sort of say that x dot, xt plus 1 equals, well, it's xt plus, some delta t for being small enough times the time derivative there, and this equals xt plus delta t f xt and ut, right? So we can kind of know how to solve this. Here, it's not really as obvious how you solve this, because you can't just add a little bit of the time derivative. You have to make sure that your next state also satisfies this equation, right? Even if your state at time t satisfies this thing, and I guess your state A control, you could also make this not a function of control, by the way. That's maybe a little more common, but because this in general is a function of control too. So even if your state satisfies this equation, and you find some control that satisfies it, you need to make sure that your state the next time also satisfies it. And that's kind of tricky, right? So let me sort of say how you go about doing this. Oh shoot, did I switch to y there? Sorry about that. I switched to using y for my algebraic variables now. That should be z everywhere. I'll just keep using z from the notation here. So here's the basic idea, though. If these equations here, this equation effectively determines what z has to be, right? Because z is p-dimensional, p. This function also is in p-dimensional. So you could essentially, if you could say invert that thing, right? You could actually determine what z is as a function. I'm kind of abusing notation here because I guess I wrote it as g hat here. So you could essentially say, what's the only z that will satisfy this equation, given x and u? X and u, right? So you could sort of essentially invert z or g rather, to find this, what z has to be. And then if you can do that, then you just z is fixed given this thing, so you just plug your z back into that one, right? So then all you just say is that, well, okay, x dot equals f x g hat inverse x u u. Okay. Of course, this is sort of not quite right, because it doesn't only have to obey this thing at this time, but it has to obey it at all times too. So you need sort of to make sure that these equations are always satisfied. But this is kind of the idea, is that you do something like this. You solve effectively for your algebraic variables, and you plug it back into the differential equation. Right? And in fact, this is actually fine. If you wanted to just ignore your algebraic variables entirely, and you can do this, this would actually remove them, right? Because then you just, at the next time, find some new x and u, and you just do this thing again. And if you can find a zt for any x and u, you're fine. Right? So then you've managed to eliminate these things from your equations. And as you might imagine, though, in practice, you often can't really invert this function. You use Newton's method to invert it, but you can't really. You have to make sure that there always will be a solution. Maybe there isn't a solution in some places. You have to make sure the state stays in a place where there is an inverse or there is a solution. So it can be pretty tricky to sort of really solve all the special cases here. And for that reason, we're not going to worry about this too much. We're really going to focus on cases where this is linear, so we can just do this trick here, where you essentially eliminate the algebraic variables. But this, I think, is kind of the fundamental idea here, is that some of the variables are given by equality constraints, some are given by differential equations, and we have to satisfy both these things as the state evolves. Now, hopefully this will actually make it a little bit more concrete here, but let's talk about one example of this, which are the operation of generators under power flow constraints. Before I do that, though, let me, for a brief period, describe what a generator looks like for now the rest of the class. I guess this is how we'll monitor. We'll describe a generator. This is actually this is essentially how we describe a synchronous generator. This is one that spins in sync with the grid, remember. And these two equations, I sort of described a little bit before what a generator kind of was, right? It was something that spun where you had to apply mechanical power to keep it spinning. That had to equal the electrical power that it needs to generate. So that sort of all is how a generator works. But this is a little bit more a formal definition. So a generator, these equations here are called the swing equations sometimes. I'll say that again, but this is sort of a very standard, simple model for a generator. So a generator is really described by two things. It's described by its power angle, which I'll call theta. People also use delta for that sometimes. You'll see both those terms for it. Sometimes in bigger power systems, they'll use delta for it. I'm using theta here. It's described by its power angle, which, remember, really is its offset from some sort of reference point, right? Because really this is, of course, changing. It's spinning the whole time. But what we care about is, we assume that there's some generator where that's 0. At a certain frequency, at least it would be 0. And assuming it's staying at a constant frequency, that this would all stay at 0. And then our angle is sort of how we compare to that hypothetical generator somewhere over there. So that's our power angle. It's exactly the things you solve for in power flow. We also, though, when we talk about the dynamics of a generator, each generator has a frequency. So in power flow, we assume that all the frequencies were all the same. But in reality, of course, they may not be the same. I mean, if they were all exactly the same, then the power angles would always stay fixed relative to each other. But if someone wants to generate more power, then some things will happen here. Now we actually see what happens dynamically. So this is the state of a generator. It has a frequency, and it has a power angle. And the equations of motion for this thing, which I'm going to write in terms of their continuous time equations, the first one's very simple, right? It just says, basically, we need to specify some function of what x dot is. So x dot, remember, equals, would then equal theta dot and omega dot. And in this case, this is pretty simple, at least for some of them. So in the first case, well, the the difference in your power angle is just the frequency minus the reference frequency. Right? That's sort of actually how we define what the power angle is. It's that thing that, you as long as you're operating exactly at the reference frequency, that power angle does not change. And if you're going faster than that, then it'll start to increase. If you're going slower than the reference frequency, it'll start to decrease. The dynamics for this one are actually also very simple, but they're getting to be a little bit subtle now. So what they are is, the way a generator works is that if we put in, if the power it is sort of, the power that's being consumed from this generator, if that is more than the electrical power, so if that's more than the mechanical power of the generator itself, the generator will start to slow down, right? So the generator has some momentum to it. It's spinning along at, say, 60 hertz. That's actually not as fast as it really is spinning, but it's spinning at some multiple of that. But say it's spinning at 60 hertz. And all of a sudden, you start turning on another light bulb. And the generator's powering something, and you turn on another light bulb. The generator won't just grind to it. It's not like that thing will just fail. The generator will not grind to a halt. What will happen instead is the generator will start to slow down a little bit. So some of that energy, which is stored up as rotational velocity in the generator itself, in order to provide the power, it needs to sort of dissipate some of that energy. So it actually will start slowing down. Similarly, if you turn a light bulb off and you can apply the same mechanical. So, and I guess what that really means is if you turn the light bulb on, then to maintain the same frequency of your generator, you will have to put more mechanical power in, right? You have to push harder. Similarly, if you turn a light bulb off and you keep the same mechanical power going, the thing will start to speed up. It'll build energy by essentially speeding the thing up. That was what conserves energy universally here. And the laws are actually for this are very simple. It is just 1 over 2h, where h here is the moment of inertia of the generator, it's the physical constant. And what you actually do is you typically just look these up in tables. So a lot of systems, say like the IEEE systems, people will actually give moments of inertia for all the generators there. So it's 1 over 2h times the power that's mechanical. That might use superscripts here. The mechanical power of the thing minus the electrical power. So this is the electrical power that it sort of needs to be that's being drawn from the generator. And this is the mechanical power that you put in. And frequency will only stay constant if the mechanical power equals electrical power. This is also ignoring friction. If there is friction, then you need a little bit extra power in addition to that. But this is ignoring any sort of drag or anything like that. These are the equations of generation, and these are called the swing equations here. And very nicely, these are linear equations, right? So assuming these things are all sort of fixed or whatever, then this is a linear set of systems, right? A set of linear equations, because these derivatives depend only on the state, I guess in this case, in a linear way. And I guess mechanical power is usually thought of as the control input you have, because you can control how much power you put on. So this is a linear function of the state and the control. And in fact, we can write this in linear system setting, right, where this is just, if we say that we can do is we can actually write x equals a, x plus b, u plus little a, because we actually do have external factors as well. But what would be the equations for this? How should I write this, actually? So actually one thing too, oftentimes people will actually just call the state the angular velocity, actually not just the angular velocity, but the angular velocity minus reference velocity. And then in that case, this time derivative is just that one. And this one doesn't change because you're just adding a constant to the rotational velocity. So you can also define the state this way. And everything stays the same here, right? Because this just becomes, so maybe I'll even write it like that. So in that notation, what is A here? What should I write in the elements of A? So this is times x. So how does this derivative depend on x? I'm defining x like this. How does this depend on x? What's this entry right here?
0.
Yes. What's this entry right here?
1.
Yep. This one here?
0.
Yeah. Right? Simple. I mean, it only depends on, the only way that the state affects the next state is that, well, the time derivative of this guy equals essentially the time derivative of theta equals this second state. So it's just this. And now I'm also going to say that u here equals p mechanical. And everything else will be external. And everything else is A. So what's B? So how does the first state depend on U? Yeah. Yep. And what's A then? What would be the affine term? So is there any constant term on this guy? Well, I'm saying that the reference is actually part of the state there. So otherwise, you'd have to have, I guess those are the same. You'd be minus omega ref there. But let's just call this the state. Because it doesn't change this one, right? So this, essentially, omega minus omega. I guess I should make this point before. Omega minus omega ref dot. This is just a constant. So this is equals omega dot. Right? So it doesn't matter whether you put that into the state or not. It all stays the same. So then what's this guy here? This is just 0. And then what's that one? Yeah, well, importantly, scaled, yeah. Negative 1 over 2h, or negative 1 p elec over 2h. OK, so this is a linear dynamical system that we have here describing a single generator. And we're actually going to come back to this when we talk about DC power flow and use DC power flow to keep everything linear. But in general, the fact is that the important part here is this term, p elec, is not really an external fixed constant. What it really is, this is determined by power flow, right? How much sort of electrical power is required, the different things, how it distributes itself, that will be determined by power flow. So the full system of equations, or at least for electrical power, the full system of equations will have other things in them. They'll have, it'll have the P I elec is the electrical power at each bus. It'll have the admittance matrices and the GIK and BIK terms for all the different buses. It'll just have the full nonlinear equations of power flow. And these, importantly, are not differential equations. These are algebraic equations, right? These are just equalities, nonlinear equalities that have to hold for all these variables. I'm using now big N to denote the number of buses. So what we can do with all this is we can put this all together. We can put together our linear dynamical system that describes how a single generator evolves together with the nonlinear equalities that describe how power flow in general evolves. And in total, you have this. I won't, actually, maybe there's no real point. I'll just point out to it rather than write it all down again. So now what we have is we have different states. So now we actually have theta I for each generator. I equals 1, 2, I'm writing this like for all I in gen. So there, not every bus is a generator, but some of them are generators. So for all the generators, we have the power at the generator. That's a state. Sorry, the power angle at the generator. That's a state variable. We also have omega I from I equals 1 to the number of generators. These are, as before, these will be our differential or state variables. These are the ones where we actually get the value from the differential equation. We also have the other things, right? We also have, well, so these two are our state variables. And they are given by the differential equation just here. Those two things. So now it's a little bit confusing because now we have a bunch of these algebraic equations here, these linear equality equations, but it's not like these are just the algebraic variables for all the states, because sometimes they're controlled. Sometimes things we actually can control. And that should probably actually, yeah, so right, so sometimes there are things that we can actually control. So what instead we have, so these are the state variables. And then what we have is, well, as with power flow, we know, for example, that PI and QI are fixed at the loads, but what we don't know is the voltage and the power angle at the loads. Those are things we have to determine by power flow equations. Similarly, at the generators, we actually, right. So at the generators, so at the loads, we don't know these things. At the generators, we don't know these things. The power angle is a state variable, but the real and reactive power are algebraic variables. So we also have these things. So we have PI elect, not PI mechanical, PI electrical, and QI electrical for I in the generators. And then at the loads, we have the voltage magnitude and the phase angle, sorry, the power angle for I being in the loads. These are our algebraic variables. And then finally, we have our controls. So this altogether equals z, this thing, and then x is this thing. And then we have our controls. And our controls here are just the mechanical power and, importantly, also the voltage magnitude. Remember, we also can control that at the generators. That we do by increasing the current through the electromagnet. These are our controls for I being in the generators. OK. So this is a set of algebraic equations. And we can sort of verify that we have the right number here, right? So we have two, I don't really say how many gens. We have 2 times the number of generators, state variables. We have always 2n algebraic variables, right? Because we have 2 for each load and 2 for each generator. And we have 2n power flow equations, 1 for real and 1 for reactive power. So we're good there. We have the right number of algebraic equations and algebraic variables. And then we have 2 controls at each generator. So this is something that at least you can describe as a differential algebraic equation. Of course, these points are a little bit subtle, right? I mean, you have to sort of realize that, OK, it really is the case that these are algebraic variables at the loads, and these are algebraic variables at the generators, because there's other, we also don't know the phase angle of the generator, but that's a state variable because we have differential equations for that one. So it's tricky because certain things are captured in power flow in certain ways, and they're captured sort of differently here. But this is really how it works. And sort of importantly, if you were a little bit confused by that like slack bus term, for example, right? That seems kind of a little bit weird. When we solve power flow, we just said, OK, one's a slack bus. It'll just pick up everything else, and that's how it works. Well, it's not really how it would work in practice, right? So it's not like there's some magic generator that just sort of knows to produce more or less power. What really happens is the generators evolve according to these laws here. And these things have to be, notice there's no slack generator here or anything like that. These are just differential equations that have to be satisfied. And so what you would get is you would get different generators that will sort of make up the slack, make up the generation that's being lost, depending on how they're controlled. So depending on how we actually control those, different generators will sort of produce power in different ways. That's sort of the basic idea here. but it's important that this is sort of the actual laws that govern power flow and will govern how they evolve. Because what really happens is that, if a load turns on or off, who will actually generate that new power would, in the ideal case, depend on how the different guys were reacting to how their power was changing, or how their frequency was changing. We'll talk a lot more about this, at least, and we'll talk about a simpler case of DC power flow when we talk about generator control in the next lecture. So I think I'll stop there, actually. We'll pick up stochastic systems next time. Stochastic systems are very important here because every real system is going to have some noise in it. You're just never going to model a system well enough, either, or there is just genuinely some actual uncertainty due to things like human intervention, stuff like that you just cannot actually determine analytically. And so, as you can imagine, things like estimation and control become harder when you have added noise in the system, especially for the case of nonlinear systems. It'll turn out that, again, when you simplify things and make them linear and Gaussian, you can actually still have optimal control and still have the best estimator you could ask for, but you can't in general. So stochastic control in general is a very hard problem, but again, we can simplify things by making everything linear. So we'll call out enough for today, and we'll see everyone on Thursday.